Hey, here's another example. It's actually measurement again, so maybe a bit redundant, but oh well. This one's involving a three-dimensional shape. So we've got a cardboard box. Okay, P.S. in case you didn't watch my part 1 video, this is B2 optimization. And there was a part 1 video that explained kind of what optimization was. So this is our part 2 video. Okay, so we have a cardboard box. It has a square base and it has a volume of 8,000 centimeters cubed. What dimensions will minimize the amount of cardboard? Okay, cool. So the first step I would take is we want to minimize the amount of cardboard. So that to me is telling us that we want to minimize the surface area of this box. Okay, so let's use some variables here for our dimensions. So since it has a square base, then we know the bottom is going to be, let's say, x by x. You know, whatever those width and length are, they're going to be the same. And then we also have a height. And we don't know what the height is or the width and length, but we know they're the same, the x's. Okay, so surface area. So how do we find surface area of a cardboard box? Okay, so let's just go through. We've got 6 sides to this cardboard box. So the top and the bottom are going to be length times width. So the top and the bottom, like this guy and this guy, the area of those two are going to be x times x. So that's x squared. And we have 2 of them, so I'm going to write that as 2x squared. Okay, plus, then we've got 4 sides, and they're going to be all the same, so I can write them as 4 whatever. So, actually, I'll just put this in another color. So the sides, these guys, there's 4 of them, and they're going to be, the dimensions are x times h for each one of them. So 4xh, I can say. Okay, cool. So we got surface area. We got a formula for surface area. But yet again, we've got more than one variable. We have x and h. So we don't want that. But we do know the volume of the box is 8,000. So that's got to fit in somewhere. So like volume of a rectangular prism is length times width times height, which will be x squared times height, because length and width are the same. And we know the volume is 8,000 squared times h. So if we isolate h, we have 8,000 divided by x squared. Okay, so we use the volume formula to isolate h, and now we can sub h in there. So our surface area formula becomes 2x squared plus 4x times 8,000 divided by x squared. Okay, that doesn't look horrible, but I mean, let's just simplify that a little bit because it does look kind of ugly. Okay, so I can cancel out an x there, and that's pretty much it. Okay, so I got 2x squared plus 4 times 8,000, so 32,000 divided by x, but I'm going to write that as x to the negative 1 since I'm going to be getting the derivative of it. Okay, so now we want to minimize that, so we're finding a critical point. So if we want to find a critical point, then we're going to find the derivative and set it equal to 0. So I'm going to find the derivative of surface area, and I'm going to set it equal to 0. So derivative is going to be 4x minus 32,000 x to the negative 2. And if I wanted to write this as a fraction, I can say 4x minus 32,000 over x squared. And if I want to make them into one fraction, I could just multiply this top and bottom by x squared. And then it would become 4x cubed minus 32,000 over x squared. If I want to combine them into one fraction, which I probably do. So then I'm going to set that equal to 0. And now I can solve it. So if I multiply both sides by x squared, that's gone. So now I have 4x cubed minus 32,000. I'll move the 32,000 over. 4x cubed. Then I'll divide both sides by 4. So I'm back to 8,000. And then I guess I'll just take the cubed root to get that. So the cubed root of 8,000 will equal x, and that's going to be 20. So x is equal to 20. Keeping negative 20 because the cubed root, negative times a negative times a negative would still be a negative. So only 20 is our only possible answer. And we could prove that that's going to be a minimum value by finding the second derivative or looking at values on either side of 20 to show that it's changing from decreasing to increasing and that it's concave up. But I don't think I'm going to do it in this video because it's going to take forever. But you could find the second derivative and prove that that's going to be a negative value so that it's, or sorry, a positive value so it's concave up. Just so we can prove that that's actually a minimum value, if you know what I'm saying. So you could find the second derivative and prove that it's greater than 0. You should probably. Okay, cool. And then let's find the height. Okay, so height is equal to, what's our height formula here? 8,000 divided by x squared. So 8,000 divided by 20 squared. So our height is equal to 8,000 divided by 400, which is 20. So our height and length and width are the same. So we got 20 meters, 20 meters, 20 meters. So it's a cube. Cool. Okay, example 3. This is a number sense example. So find two integers with a sum of 20 and whose product is a maximum. All right, so let's let x represent one number and y is the other number. Okay, so two integers. Okay, so we have a sum of 20, so x plus y equals 20. And then we want the product of those integers to be a maximum value. So we want x times y to be a maximum. Or maybe I'll put a p for like product. So those are two equations. So we're going to work with this one because that's what we're trying to maximize. But again, I don't want to work with two variables, so let's isolate one of these guys. So say I isolated y, then I have 20 minus x, and then I just sub that in for y. So p is equal to x times 20 minus x. And then I'm just going to expand that. So I have 20x minus x squared. And now let's take the derivative. So derivative is going to equal 20 minus 2x. And then I'll set the derivative equal to 0 to find my critical point. So 2x equals 20. So therefore x equals 10. And then if I want to find y, I just do 20 minus x. So y is also 10. Wow. These questions that I've shown in my examples are all like the same number. So therefore the two integers are 10 and 10. Always good to answer the final question. And that will give you a maximum product. And they add to 20. Okay, cool. So that was an example of a number sense kind of question. A really easy one though. Okay, more to come.